Okay, question 13. So, in the southwest region of England, 100 households were randomly selected. For each household, the weekly expenditure X pounds per person on food and drink per week was recorded. The maximum amount recorded was £40, 48p, and the minimum amount recorded was £22. The results are summarised below, where X bar denotes the sample mean. So we got sigma X is £3,046 14p, and sigma X minus X bar squared is £1,746 29p. Part A wants us to work out the mean and the standard deviation. So the mean X bar is sigma X over n. So here that's 3,046.14 divided by 100. Now that, if we go to 2 decimal places, is going to give us 30.46. Now, for the standard deviation, we are given a formula for it in the booklet. Here it is. That, though, is when we're looking at population. We are looking at a sample here. So the only difference is that S is the square root of X minus X bar squared over n minus 1. So we get the square root of 1746.29 over 99, and that is going to give us 4.199 blah blah blah, so let's call that 4.2. Cool. Okay, A part 2 says, using your results from A1 and other information given, explain why the normal distribution can be used to model X. Okay, so first of all, to use the normal distribution, data must be continuous. So this data can be considered as continuous as required, and what we also need is the minimum and maximum amounts recorded to be within the mean plus or minus 3s, so 3 lots of the standard deviation. So X bar add 3s is, using our numbers, 30.46 add 3 times 4.2, which gives us 43 0.06 and x bar minus 3s is going to give us 17.86. So we know that our minimum and maximum amounts were £22 and £40.48. So also the minimum and maximum recorded amounts are contained by why do I always run out of room? Are contained by x bar plus or minus 3s. So that is the two reasons why we can use the normal distribution. Okay, part 3 wants us to find the probability that a household in the southwest spends less than £25 on food and drink per person per week. So, our calculators can do this. Let's set up the distribution. So, x is normally distributed. Now our mean was 30.46. And our variance is our standard deviation squared. So 4.2 squared. Now we want the probability that x is less than 25. So on your calculators, go to distribution and then normal CD. Now we want our lower to be, well, it doesn't actually really matter. Let's have it as, I don't know, minus 100, just so that it's far enough away from the info that we are playing with. Our upper bound is 25, because that's what we want the probability of being less than. Sigma is 4.2 and mu is 30.64. No, it's not 30.46. So plug all of that in and I get 0.0968. Cool. And for part B, in the northwest, for households in the northwest of England, the weekly expenditure, £5 per person on food and drink, can be modelled by a normal distribution with mean £29.55p. It is known that the probability that x is less than 30 is 0.55. We want to find the standard deviation of y, giving our answer to 1 decimal place. Okay then, so what do we know? Well, we know that y is normally distributed with a mean of 29.55, but we don't know the standard deviation sigma. That's the aim of the game. So what we do know is, remember that the probability is area under the curve. So if we draw a little sketch of what's going on there, then our mean is slap bang in the middle, so there's 29.55. Now we know that the area less than or up to 30 so all of this area in here is 0.55. So we can use our calculators here with the inverse normal to find the value of z. So I'll put it up on screen what I've done with the inverse normal. So we set the area as 0.55, sigma as 1 and mu as 0, because when we're dealing with z we have standardized the distribution. So we will get then that z is the inverse normal of 0.55, which is 0.1257. Now we also know that z is equal to x minus mu over sigma. Now 3 out of those 4 things we know. So we know z is 0.1257. We know x is 30. Mu is 29.55. And then we don't know sigma. So if we multiply through by sigma and divide by 0.1257, up on top we get 0.45 divided by 0.1257, which does, to one decimal place, give us 3.6. Go.